Hello everyone! Today we will learn about advanced counting techniques. Firstly, what are recurrence relations? In mathematics, a recurrence relation is an equation that represents a sequence based on some rule. It helps in finding the subsequent term, next term, dependent upon the preceding term, previous term. If we know the previous term in a given series, then we can easily determine the next term. For example, let n be a sequence that satisfies the recurrence relation at n equals at n 1 plus 3 for n equals 1, 2, 3, 4, and suppose that a 0 equals 2, which is initial condition. What are a1, a2, and a3? Here is the solution. Next, we move to the application of recurrence relation. There are three of them. First, Fibonacci numbers, second is Tower of Hanoi, and the third is counting problems. We go to the first application, which is Fibonacci numbers. The Fibonacci sequence, also known as Fibonacci numbers, is defined as the sequence of numbers in which each number in the sequence is equal to the sum of two numbers before it. Here is the Fibonacci sequence. Here, the third term, 1, is obtained by adding the first and second term, which is 0 plus 1 equal to 1. Similarly, 2 is obtained by adding the second and third term. 1 plus 1 equal to 2. 3 is obtained by adding the third and fourth term. 1 plus 2 equal to 3, and so on. For example, the next term after 13 can be found by adding 8 and 13. Therefore, the next term in the sequence is 21. Then, we use rabbits as an example for the Fibonacci number. A young pair of rabbits, one of each gender, is placed on an island. A pair of rabbits do not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month. Find a recurrence relation for the number of pairs of rabbits on the island after n months, assuming that rabbits never die. Here is the solution. Let Fn be the number of pairs of rabbits after n months. There are is F1, which is 1 pairs of rabbits on the island at the end of the first month. We also have F2, which is 1 because the pair does not breed during the first month. To find the number of pairs on the island after n months, add the number on the island after the previous month, Fn minus 1, and the number of newborn pairs, which equals Fn minus 2, because each newborn pair comes from a pair at least 2 months old. Consequently, the sequence Fn satisfies the recurrence relation Fn equal to Fn minus 1 plus Fn minus 2, for n is greater than and equal to 3 with the initial conditions F1 is 1 and F2 is 1. The number of pairs of rabbits on the island after n months is given by the nth Fibonacci number. Next, we move on to the second application, which is Tower of Hanoi. The Tower of Hanoi is a mathematical game or puzzle. It consists of 3 pegs and a number of discs of different sizes, which can slide onto any pegs. The puzzle starts with the discs in a neat stack in ascending order of size on one peg, the smallest at the top, thus making a conical shape. Rules: you are allowed to move the discs one at a time from one peg to another as long as a larger disc is never placed on a smaller. Goal: using allowable moves, end up with all the discs on the second peg in order of size with largest on the bottom. So, the solution is let Hn denote the number of moves needed to solve the Tower of Hanoi puzzle with n discs. Set up a recurrence relation for the sequence Hn. Begin with n discs on peg 1. We can transfer the top n-1 discs, following the rules of the puzzle, to peg 3 using Hn-1 moves. First, we use one move to transfer the largest disc to the second peg. Then we transfer the n-1 discs from peg 3 to peg 2 using Hn-1 additional moves. This cannot be done in fewer steps. Hence, the sequence is Hn equal to 2Hn-1 plus 1. The initial condition is H1 equal to 1 since a single disc can be transferred from peg 1 to peg 2 in one move. This is another example of how to find the formula. This way is easier to understand how the Tower of Hanoi works. We can see the pattern here from n equal to 1 to n equal to 4. And from the pattern, we can form the formula. For the last application is the counting problem. Here, we are counting the bit strings. A bit string is a string of bits that consist of numbers 0 and 1. The length of a bit string is the number of bits in the string. An example of a bit string of length 4 is 0010. For another example, a bit string of length 5 is 11010. For this example, we need to find the recurrence relation and give initial conditions for the number of bit strings of length n without 2 consecutive zeros. How many such bit strings are there of length 5? So, the solution is let's n denote the number of bit strings of length n without 2 consecutive zeros. To obtain a recurrence relation for n, note that the number of bit strings of length n that do not have 2 consecutive zeros is the number of bit strings ending with a 0 plus the number of such bit strings ending with a 1. Now assume that n is greater and equal than 3. The bit strings of length n ending with 1 without 2 consecutive zeros are the bit strings of length n minus 1 with no 2 consecutive zeros with a 1 at the end. Hence, there are n minus 1 such bit strings. The bit strings of length n ending with 0 without 2 consecutive zeros are the bit strings of length n minus 2 with no 2 consecutive zeros with 1 0 at the end. Hence, there are n minus 2 such bit strings. We conclude that n equal to a n minus 1 plus a n minus 2 for n greater or equal than 3. The initial conditions are a 1 equal to 2, since both the bit strings 0 and 1 do not have consecutive zeros. A 2 equal to 3, since the bit strings 0 1, 1 0, and 1 1 do not have consecutive zeros, while 0 0 does. To obtain a 5, we use the recurrence relation 3 times to find that a 3 equal to 5, a 4 equal to 8, and a 5 equal to 13. From that, we can see that actually a n satisfies the same recurrence relation as the Fibonacci sequence. Since a1 equal to f3 and a2 equal to f4, we conclude that an n equal to fn plus 2. That's all from me. I hope that this video can help everyone with the advanced counting techniques topic. Thank you and goodbye.